next topic we're going to talk about is something called a rate law. It is an equation that describes how the rate of the reaction depends on the concentration of the reactants. Okay, so we're going to use the same example as we did to illustrate reaction rates. And remember that we did an experiment, so I'm going to call it experiment 1. And we got the rate of reaction, average rate, and that was 0.0018 molar per second. And that was when NO2 started out at 1 molar. Okay, so we're going to put a little subscript 0 on the square bracket. The square bracket is what we're going to use for notation for concentration and molarity. So the initial concentration was 1 molar. Okay, so a rate law looks something like this. So the rate of reaction, which we'll just call rate, is equal to a constant K times the reactant molarity to some unknown power. So we're going to call it unknown power Z, and the only reactant we have is NO2. So in more complicated examples, we'd have, if we had 2 reactants, we'd have 2 square brackets, 2 exponents to determine, and so on. And of course, we'd need a lot more experiments to do that. Okay, so now let's think about what the exponent should be. Well, if you're new to this, of course, you would think, well, this must be 2 because this is 2 in front of the NO2. Well, that's actually not necessarily the case. It could be the case, but what we have to do is actually have to determine through experiment what actually is going on. And so the way to do that is to take the initial concentration and we're going to change it. So just imagine that we got one experiment already, and we're going to write down the rate is equal to a constant times the molarity, which we already have, to unknown power Z. All right, so once I have a number, it's good at practice to actually make it a parenthesis. So let me erase that first bracket and make it a parenthesis. Okay, so we obviously don't have enough information to determine both the unknown constant K and the exponent Z. Well, what we can do is another experiment where we change NO2 to be half of what it was. And so if this is going to be half of what it was, then the rate is going to be 1/2 to the power Z. So this is what we're going to do. So we change the initial concentration of NO2. We run the experiment. We take the slope. We get the rate of reaction from all that. And the answer we should get, if this reaction occurs in nature as we see, it's a good deal slower. It's 0.00045 molar per second. All right, so let's go ahead and put that down below here. Okay, so all we're going to do is actually take this equation and divide it by this equation. All right, and so if the left-hand sides are equal, then we get 0.0018 divided by 0.0045, and we get 4. We get K over K, well the K's over K is 1. We get 1 over 0.5, which is 2. And since they're both raised to the Z power, we get 2 to the Z power. Now this is a very easy equation to solve. Okay, so if you're smart, you'll pick some sort of nice even integer ratio for these two starting molarities. You'll put the larger one on top unless you really like to work with fractions. So put the larger one on top, and so I get a 4 equals 2 to the z power. You saw that by various means. The easiest thing to do is by inspection. So it turns out that, yes, our naive guess that it would be 2 is true, but it's only by coincidence. There could be an actual reason for that, or there are actual reasons, but there are several possible reasons, one of which is that this could occur in one step. If this reaction occurs in one step, then the powers that you get in the rate law expression do reflect the stoichiometry. But again, you don't know that until you actually do the experiments. All right, so this is called the method of initial rates because you're measuring the rate of the reaction from time 0 to some short time afterwards. And the reason you do the initial rates is to avoid any sort of interference from products that are being made. And as we will allude to later, actually in some chemical reactions, the products can actually recombine to form reactants, and that will mess up your rate of a disappearance of the reactant. Okay, so that's a simple example of the idea behind how you get the rate law, which is rate equals K times reactant concentrations to some sort of powers. In general chemistry, we're only going to see integers for these powers. And so if the exponent is 0, of course, we don't generally write something to the 0 power is equal to 1, but we'd say it's 0 order in that particular reactant. Or if the exponent is 1, generally you don't write the exponent if it's something to the first power, but that would be a first order. And this example here, since the exponent is 2, is a second order chemical reaction. Now the thing we need to do now is actually solve for the rate constant K. Now we can use either the first experiment data or the second experiment data, and we should get the same answer no matter which one we use. So let's go ahead and pick the second one. Why not? All right, so 0.00045 molar per second is equal to K times 0.500 molar squared. Okay, so we're going to square this and get 0.25. And then we're going to divide both sides by this. All right, so molar to the first power divided by molar squared, we're going to get molar to the minus 1. And so the rate constant, which we have now determined, is a positive number because the rates of reactions by definition are positive numbers. Remember that. So K should always be a positive number. The other thing is that depending on what the exponent Z is, that's going to determine the exponent of M. So if it had been a first order reaction, there would be M to the 0. If it had been 0 order reaction, it would have been M to the first power, and so on. So it's very important for you to realize that the units of K do depend on the order of reaction. And it's critical for you to get them right, because frequently that's a clue to the actual order of reaction. Now there is one more thing we can talk about as far as the rate of reaction. And it has to do with the laboratory. All right, and so what we can do with this reaction here is take the natural log of everything. Okay, so when we do that, we're going to get natural log of the rate is equal to Z times the natural log of NO2 plus the natural log of K. Okay, so here we're using a couple of properties of the logarithm. Log of a product is the sum of the two logs, and then the log of something to a power is the power times the log. And so when we do this, so what you would do in the laboratory is you'd measure the rate somehow, and then as a function of the reactant concentration, and then take your rate number that you get, take the natural log, take the concentration you started with, take the natural log, and plot those numbers. This is a y. That's your slope. This is your x. And there's your intercept. All right? And so in this particular experiment, you should get a slope of 2 if you use the experiments for this particular reaction. All right, well that does it for that topic. On to the next.